In this video, I'm going to work through two examples of evaluating a trigonometric expression that now also involve double angles or the use of compound angle formulae. Now, if you look at this question, it says evaluate, and then we have a fraction, and in that fraction, in the numerator, I have sine 35 degrees times cos 35 degrees, and in the denominator it's tan 225 degrees times cos 200 degrees. Now, previously, you would look at this and you need to use your special angles if possible, so you use reduction formulae and ideally are able to cancel out any trig functions or use special angles to find value of this. Okay, but if you try that, you're going to get stuck with this one. So we expand our toolbox by including double angle formulae and compound angle formulae. Okay, so if we look at this carefully, in the numerator I have sine 35 degrees times cos 35 degrees. Now that looks like the sine double angle. Okay, the right hand side has a product of a sine angle times cos of the same angle, which is what I have there. The only thing that's missing is the coefficient 2. Okay, but as in previous examples, we have seen that we can actually insert the 2 if we also multiply by a half, because a half times a 2 is 1, so we're not changing the value of the expression. So I'm going to work with my numerator first. So if I insert the coefficient of 2 to have the 2 sine 35 degrees times cos 35 degrees, in order to get the full sine double angle expansion, I do also need to multiply by a half to ensure that I'm not changing the value of the expression. Okay, now I move from my numerator and look at the denominator. Now in the denominator I have a tan. Now tan does not form part of any of the formulae here. Okay, and I notice also that the two angles, 225 degrees and 200 degrees, are different. Okay, so we notice the different angles and that I have a tan. Now remember that tan theta is equal to sine theta over cos theta, which is our quotient identity. So I can rewrite tan in terms of sine and cos, and thereby at least getting rid of this third trig function. Okay, but what we do want to try do is be able to simplify somehow. So we are going to reduce the angles to see where that takes us. Okay, so tan 225. Now 225 is in the third quadrant, and in the third quadrant I can rewrite my angles as 180 degrees plus an angle that would get me to 225, which is 45 degrees. Okay, then I have cos of 200. 200 is in the third quadrant, in which I write my angles as 180 degrees plus an acute angle that would get me to 200. And I am now able to apply the reduction formulae there. But first, looking at the numerator, what I have in brackets is the expanded form of the sine double angle, so I am able to contract it, and it goes to sine 2 times 35 degrees. Right, in the denominator, tan is positive in the third quadrant, so the tan 180 degrees plus 45 reduces to positive tan 45 degrees, and that is the special angle of which I can know its value. Okay, times cos in the third quadrant, however, is negative, so this is going to reduce to negative cos 20 degrees. Okay, so let's keep simplifying and see what we are able to do. With these types of questions, it is often not obvious what exactly you need to do. So you need to actually just go in and try something. Know that your toolbox consists of your identities. As mentioned, I've got the quotient identity. Here, keep in mind, you've also got the square identity. You have your special angles and you have your double angle and your compound angle formulae. So that is your toolbox, and you need to just try things and see how they simplify. If they don't work out, you go back and you try something else. The more you try, the more you practice, the more you get your eye into knowing actually what to do, and then it becomes easier. Okay, so in the numerator, it simplifies to a half sine 2 times 35, which is 70 degrees. Tan 45 degrees is a special angle which we know is equal to 1. Then I still multiply negative cos 20 degrees. Okay, now I need to evaluate, which means I need to find the value of this. So I cannot just leave it like this. So if we look, I see I have sine and cosine. Now they are co-functions of each other. Okay, so I could try reduce one to its co-function. Okay, and I see that 70 and 20 are complementary angles, so it will actually work out nicely. Okay, so you can choose to reduce cosine 20 degrees to its co-function or sine 70. Let's just go with the sine 70 in this case. Okay, so sine 70 can be rewritten as 90 degrees minus the angle that would give me a value of 70, so 90 minus 20. In the denominator, I'm left with negative cos 20 degrees. Okay, now in the numerator, I have a half. Now sine 90 minus 20, the 90 indicates to me that I'm going to reduce to the co-function. This is in the first quadrant, so every trig function is positive, so it reduces to cos 20 degrees. Okay, then in the denominator I have negative cos 20 degrees, so because I have one term, I can now cancel my common factors, and I'm left with negative a half. Right, second and final example in this video. I have to evaluate an expression again, and in this expression I have a fraction minus a fraction. If that is the case, the first thing you want to try to do is rewrite it as one fraction with a lowest common denominator. Okay, so I have sine 36 degrees over sine 12 degrees minus cos 36 degrees over cos 12 degrees. Okay, so my lowest common denominator will simply be sine 12 degrees times cos 12 degrees. Okay, now take note of that denominator. Okay, I have a product of a sine and a cos function with the same angle, which again reminds me of the cos double angle formulae. I would just have to make sure that I have a coefficient of 2 by multiplying a half times the 2. Okay, but my numerator, so to get this denominator to the common denominator, I had to multiply by cos 12 degrees. So I'm going to do the same to the numerator. So I have sine 36 degrees times cos 12 degrees minus, to get the second denominator to the lowest common denominator, I had to multiply by sine 12 degrees. So I'm going to do the same to the numerator. So I have cos 36 degrees times sine of 12 degrees. Okay, so if I now look at the numerator, it is sine 36 degrees times cos 12 degrees minus cos 36 degrees times sine 12 degrees. Okay, now I notice that I have two terms. In each term I have a product of a sine times a cos, sine times a cos. Okay, but it's sine, cos, cos, sine, which reminds me of the sine compound angle formulae, and the angles are the same. So I've got 36, 12, 36, 12. Okay, so because I have that minus there, I'm going to look at the sine angle minus an angle. Okay, because remember, for sine the angle doesn't change. Okay, so in my numerator, those two terms and that expression of the numerator can be contracted using the sine compound angle formula to sine of 36 degrees minus 12 degrees. Okay, looking at the denominator, I've already mentioned that this looks like the sine double angle, but it's missing a 2, coefficient of 2. Okay, But if I just write that in, it changes the value. So in order to avoid changing the value, I multiply by a half, because a half times 2 is 1. So I'm not changing its value. But now what I have in the brackets is the expanded form of the sine double angle. Okay, so in the numerator, it simplifies to sine 36 minus 12 is 24 degrees. The denominator simplifies to a half, and then the double angle there contracts to sine 2 times the angle. Okay, so I have sine 24 degrees over a half times sine 24 degrees. Those cancel nicely, and I have 1 divided by a half, which is 2.